Okay, yeah, so thanks for the invitation to give a talk. And this is some work that we have been doing with this not quite a football team of collaborators. So that's Vijay Balasubramanian, Alice Bernamonti, Jan de Boer, who was here last week, Ben Krabs, Lasse Franti, Federico Galli, myself, Bernd Müller, and Andreas Schäfer. And it's not quite a football team because we don't have any defenders or goalkeepers whose task would be to prevent other teams from scoring. But instead we have two strikers, and I guess the strikers of the team would be Alice and Federico. Okay, so this is a study of inhomogeneous non-equilibrium dynamics using a model, a holographic model that has the benefit of being almost analytic. So let's see what we find out from this. So first a few words for the original motivation for this work. So the motivation comes from heavy ion ultra-relativistic heavy ion collisions. So let me just review some basic notions of that. So in these collisions of nuclei, kinematics plays an important role. So first of all, there's Lorentz contraction, so that the nuclei are contracted in these thin pancakes, as you know. And also, there's a very high Parton density, and the Parton wave functions overlap significantly. And also because of time dilation, the number of virtual gluons becomes significant at the scales probed by the experiment. And so there are many long-lived gluons, and when they actually dominate the system, so that the valence quarks play very little role. Now these gluons interact, and the interactions are nonlinear, and you would think that this is a horribly complicated process to describe, but fortunately it turns out that the effect of the nonlinear interactions is that the system becomes phase coherent, and you can model it by essentially a classical field, and that's the so-called color glass condensate model. So the color glass condensate, or CGC, can be used as a model for the initial stage of the gluons in the collision. Now, maybe I should go back to this slide. So then, after you form the initial state, then there's a period of where the system is highly off equilibrium, and then it fast settles into a regime where hydrodynamics can be applied, and then there are lots of good codes for doing hydrodynamic simulations in this system, and then the system hadronizes, and then you have this stuff flying out in the end. So, what's the not so well understood part of this process is the far from equilibrium dynamics before the hydrodynamic regime. So let me describe of another thing that was that's one of the discoveries at LHC recently. So it used to be that there's this idealized picture of the collision. So you have these pancake-shaped nuclei that are colliding, and typical collisions are non-central, so that there's some overlap between them. And then there's this idealized picture that after the collision, the interaction region has this almond shape, and due to this elongated shape, then there are pressure gradients, which tends to drive the flow more in these directions and less in those directions. Now, if you take the reaction plane, you can introduce some coordinates. There's this angle phi, the azimuthal angle, and then you can look at the in the experiments you look for the azimuthal particle distribution, which can be Fourier expanded in this angle phi. Now the angle psi n is subtracted because different collisions are tilted with one another, so you have to, it's sort of the angle of the reference plane, and then phi is with respect to that reaction plane. Okay, so the first non-trivial coefficient V2 is the so-called elliptic flow coefficient that results from this almond shape. But recently it was discovered that, by the symmetry of by the reflection symmetry about the y-axis, you would think that there are no odd coefficients in this expansion. But it turned out that they are actually there, and they are even large. Now, that means that the system cannot be as idealized as this, but event by event in the collisions, there are some fluctuations which create some asymmetry, and that results into these higher coefficients. So here's a picture of which is a bit more realistic. So depending on how the partons are distributed inside the nuclei, the dominant symmetries, instead of being elliptical, they could be triangular, so that you get triangular flow, and so on and so forth.
So these pictures, they are numeric, so it's experiment or?
Probably some simulation. The reference is this paper by Young, who let's check that for details. Okay, so so what you want to do is that first you would like to compute for some statistics for the initial deposition of energy, and this can be done by using the class clone condensate picture, and our collaborators have done some calculations for statistical analysis for the energy deposition. Now, then on the other hand, you have the regime where viscous hydrodynamics becomes applicable, and then you have nice codes for evolving the system. And of course, what you need is the initial state, or the probability distributions for the initial states. So the question is that how do you connect this information, which comes from the CGC, over through the non-equilibrium phase to the regime where hydro takes over, so that you translate this initial information to the initial information for the hydro code. Now, what people often do is that they just model this this transitory phase by something simple, just free streaming, so that these energy depositions just flow freely and for some time, and then you come to the time where you take the state and feed it into the hydro code. Okay, so the question is that how well is this strategy justified? Is free streaming is free streaming followed by hydro really a good description of this system? So it's a strongly interacting system. Famously, it's like an almost perfect liquid with small viscosity, and people have been using, as you know, holographic models to model this system. So the question is that can we gain any insight from holographic studies, in particular to this question, that how good an approximation is for this non-equilibrium dynamics or highly off equilibrium dynamics is this picture of free streaming followed by hydro. Okay, so let me remind you of some rules here. So in field theory, suppose that, as you know, if you take a 3 plus 1 dimensional n equals 4 super Young Mills, at large n and at large Toft coupling, you can approximate the system with gravity and ADS 4 plus 1. But instead, we will be working in ADS ADS4, four-dimensional anti de Sitter space, because that's easier. And then the dual system is a 2 plus 1 dimensional plasma, which Chris Herzog talked about last week. So that's the ABJM theory. And then finite temperature corresponds to having a black brane in the bulk, or in the anti de Sitter space, with the Hawking temperature being that of the dual field theory. And fluid dynamics or hydrodynamics corresponds to long wavelength perturbations of the black brane geometry. But then if you start with highly off equilibrium and the system thermalizes, then you must start with something which undergoes a gravitational collapse and forms a black brane.
But here you are not interested in ABJM, right?
I'm not interested in the details of ABJM, so all the details of the theory doesn't matter. So I will just study some 2 plus 1 plasma by using this side. Okay, so there are different models for heavy ion collisions. The one that I will be focusing on is the dual geometry, so-called ADS-YDS spacetime. And in field theory, it describes basically starting out in a vacuum and then injecting energy in a homogeneous and isotropic way. I will discuss that in more detail. But then there are lots of other studies where you consider anisotropic injection of energy, like for instance by Chesler and Jaffe. And there are boost invariant models that Yannick and collaborators have been studying, colliding shock waves, and possibly other ones that I don't recall right now. Now, these other ones have more realistic symmetries as pertaining to the heavy ion collisions. But then on the other hand, the price that you have to pay is that you have to study these systems numerically. And on the other hand, the first one needs no numerics. You can do a lot of stuff analytically. So that's why it's a nice toy model, and that's what I'm going to be focusing on. So what is the ADS-Y geometric? Well, it describes null collapse of null matter that falls along light rays, and then it crosses its horizon to form a black hole or a black brane if you take the horizon to be flat. And the metric is astonishingly simple. It is just the all non-trivial information is in this mass function that depends on the one of the null coordinates that you can think of as the time coordinate. It actually is the time coordinate at the boundary. And depending on how you build the null matter shell that collapses, if you just take some bump, for instance, that gives rise to a simple mass function where you start with 0 and then you exponentially grow to saturate the final mass. Okay, so in this picture, the geometry is on this side before the null matter is introduced, just pure ADS space and vacuum in the boundary. Then you source the boundary, then having the null shell collapse corresponds to turning on some source that injects energy for a tremendously short time, so that you could think of some homogeneous and isotropic explosion happening at the boundary. And the system is at highly off equilibrium state, and then it thermalizes. And it actually thermalizes very rapidly and to the black hole temperature set by the final mass of the system.
In this model, thermalization is already inside the model, right?
Yeah, it's inside the model. But okay, let me talk a little bit more about that. Well, when you say thermalizes, then you have to always ask that what is the observable that you are studying, because different observables see different things. Now, for instance, if you just look at yes.
Can you go back to the previous?
Yes.
So, yeah, the diagonal lines there are the Cauchy horizons
ADS, right? So you have here this line, this diagram. So these are so in principle you can extend across the line that's like this, right? You can, so how does the singularity extend into that region?
I haven't thought about that question, so yeah, I don't know.
Does it extend or not?
Well, I haven't actually thought about that at all. So because I'm mostly interested in this region outside the horizon. So
No, it's just because it would matter where the horizon is if the singularity extends within that point.
okay, well, maybe we can discuss this later because I'd be curious to learn some more about it. Okay, but anyway, for most observables, what matters, like if you look at expectation values of local operators, then the expectation values, like in the previous talk, it was mentioned, is just given by the subleading fall of a dual bulk field that couples to the operator. And then when you solve the field equations, then you just look at the profile of the field very close to the boundary. And so that what happens deeper at the horizon doesn't matter. And if you are somewhere here, then the region near the boundary is that the geometry is just that of a black brane. So therefore, these one-point functions would be instantly thermalized. Now, for example, the stress tensor can be read off from the metric. There's a little bit of detail that, that has to work through. There's this process called holographic renormalization. But then, in particular, the metric near the boundary is that of the black brane, so the stress tensor takes the form. It's just thermal after the injection. But in fact, the system is not just completely instantly thermal, because if you look at some other observables, like if you take an expectation value of a non-local operator, like a Wilson loop, or if you look at, instead of looking at one-point functions, if you look at two-point or higher point functions, then what happens is that you will, for these computations, you need information from deeper in the bulk, and it may be that although you are calculating the observable here, the information about the bulk geometry extends across the falling null shell to the vacuum side. So therefore, you can see that the metric is just not that of a black brane, but is more, and as a result, these observables are non-thermal. And then you can study that for these non-local observables, how long do you have to wait before they just involve the region which is completely inside the black brane geometry, or described by the black brane. And the answer is usually that not very long. The typical time scale, typical time scale involved is very short. It's basically just the inverse temperature. Okay, so then now let's study this a bit in more detail, or Bhattacharya and Minwalla studied the model in more detail. They did a self-consistent analysis where they made this collapsing null shell from a massless bulk scalar field. So what they studied is that they studied Einstein scalar equations with the negative cosmological constant, and they studied this process where they give some initial profile with a small amplitude epsilon for the bulk scalar field. They use that as a boundary condition in the equations and other boundary condition, and then for initial condition they use that the space-time is just pure ADS. And then they solved the field equations perturbatively in the amplitude epsilon. And what they find is that as a result, well, when you turn on the source, then you send in a scalar field shock wave, and always a black brain will form, even for small amplitudes. So what you find is that at late times, the mass of a forming black brain goes like epsilon squared over the time for which the source was turned on.
One question.
Yes?
I'm not an expert, but to what extent can we believe that? It's just for very short times, because this is a perturbative analysis. So we can really believe that we are going to have black brain formation always. Just using some kind of very simple.
Okay, so that brings me to the next question. That it might be that since you are doing this perturbatively, then you have to worry about the expansion becoming uncontrolled. And yeah, this naive approach. Okay, well, let me just go to the next next one. So
This orientation. So the
yes,
temperature, can you go back to the previous slide? The temperature going like epsilon 2 divided by V divided by delta T, whatever. It's just like the energy you screw initially in converts completely into temperature. Is that the way to read it?
yeah. And the energy depends on the. You have to calculate the energy momentum tensor of the scalar field, and that's then the source for the the right hand side in the Einstein equation, and then you just solve. Yes.
If in this picture, anything if it is very local is already thermalized even before any black hole is formed, right?
Even before a black hole is formed.
Right.
Well, you mean that if you are here, then you would argue that, well, that's well before the horizon.
Yeah, anything,
And
even before any
yeah.
the interaction, is relevant. So no interaction is relevant for any, I guess.
Yeah. For since the system is homogeneous, then this is what happens. That the one-point functions of local observables would appear to be thermal. Well, it's a bit. It's a bit mysterious. This model is a bit mysterious in that sense. But that's why I want to go to inhomogeneities, where then it's not so clear what happens. So
before you do that, one more
Yes.
question.
Yeah.
Why in this model don't we see a scalar quasi-normal mode, which is homogeneous, that damps on a thermal time?
let me come back to that.
Okay.
Yeah. Okay. So the question is that we don't see them because the naive perturbation theory breaks down before you get to that stage.
What do you mean quasi-normal mode?
Okay. Well, let me try again. So first of all, there are these two perturbation theory approaches that Bhattacharya and Minwala used. There's the naive theory, where you just start with the ADS vacuum, and then you, as a background, where you do the expansion. And as pointed out, usually you might worry about the perturbative series growing, and in fact, some various coefficients grow actually polynomially in time. But the relevant parameter is V times the temperature. So if you are, if you stay to times which are less than the inverse temperature, which is anyway larger than the time scale of injection, because there was this small amplitude in the denominator. So there is a time window for which this is reliable, and you can make the time window larger by considering smaller amplitudes. But then for late times, you find that this will diverge. Okay, so now what's more clever is to reorganize the perturbation theory a little bit like what one does in field theory at finite temperature, where you also have divergences, but then you can adjust for that by modifying the propagators. Like, for instance, if you work with working QED at finite temperature, you know that the photon gets a thermal mass, so you modify the propagators by putting the thermal mass into them, and then you redo the perturbation theory where you treat the couplings inside the masses exactly, but the couplings everywhere else are used in a perturbative manner. So likewise, what Bhattacharya and Minwala did is that they, instead of taking the ADS vacuum as a background, they take the ADS Vaidya metric as the background for the expansions. And then they work exactly in where the masses appear, and of course the mass, well, it secretly depends on the amplitude squared, just like the photon mass depends on the coupling squared. So, but they work perturbatively in other appearances of the small expansion parameter. And by this way, they obtain a solution that's reliable outside the event horizon. And then they find that at late times, indeed, observables decay exponentially to thermal values.
So if I want to reconcile that with the claim that the first perturbation theory gives exactly ADS Schwarzschild after a finite time, it must be that the amplitude of the quasi-normal modes is small in epsilon. As epsilon goes to 0, the amplitude gets very small in some sense. Is that true?
That would be. I don't remember what they said about quasi-normal modes in the naive perturbation theory. So we can discuss that later.
Quasi-normal modes work when the energy in the quasi-normal mode is much less than the temperature of the. In fact, if you already start in a finite temperature solution, it has to be less than the initial temperature. Then the quasi-normal mode is very well defined as perturbation around Schwarzschild. But here, if you start around in a state where you don't have Schwarzschild to start with,
yeah.
any energy or any amplitude you put in whatever mode will give you trouble.
Right. So the confusion was that it claimed in some context to have exactly ADS Schwarzschild after a short and finite time, and clearly perturbing around that final solution gives a quasi-normal mode that decays the thermal time. Reconcile the.
Yeah, I guess also then you would need to have a reliable geometry, I guess, all the way down to the horizon. But the question is that whether the solution is reliable deep enough in the bulk.
So that's, I mean, this arrow says ADS black brain metric, which I understood to be the exact metric
okay, well,
in that triangle. And you said that arrow is not referring to that entire white triangle that includes.
Sorry for that. Yeah, this was a bit too quick. So there's more detail about these expansions and so on. So
fine.
You know, because So now I want to come to the to what's new. So it's basically just an inhomogeneous variant of the calculation of Bhattacharya and Minwala. So, by the way, one thing that I should say is that life is easy if you take D, the space dimensionality, to be odd. And in particular, they obtained explicit solutions for D equals 3. So meaning that the boundary is 2 plus 1 dimensional.
Is there any simple reason and that why there are difference between odd and even?
Some technical reasons that I'm unable to reproduce right now. So maybe somebody else.
I thought it was mostly the propagation on the light cone in even space-time dimensions versus the off-shell, versus the fact that in odd space-time dimensions the Green's functions fill the light cone.
Okay.
Wasn't that the main?
Yeah, that sounds.
Yeah, so it's a standard uneven difference in
Okay.
propagation for massless fields.
Okay. All right. So so the boundary has 2 space dimensions, and of course, what I would like to do is to consider generic inhomogeneities, but that just means that I will need more components of the Einstein scalar equations. So in order to simplify things, I consider a source which is translationally invariant in y direction, but inhomogeneous in x direction. And so now I add this x dependence. And then on top of the amplitude expansion, I'm going to do a gradient expansion, which means working in the long wavelength limit. And so I assume that the scale of spatial variations is a lot longer than the thermal wavelength. So the goals here is to extract the stress energy tensor and then study its time evolution, and then compare the distribution of energy and pressures with models, with other models like free streaming, and then in particular I would like to study when does the onset to viscose hydro happen in this picture. Okay, and well, in this case we are limited to so far working on just on naive perturbation theory. So we are taking the vacuum as a background. So we know that this is not going to be valid for arbitrarily long times, but instead, again, there's this upper limit that as long as you work for times that are less than the inverse temperature scale, which on the other hand is less than the scale of spatial variations, then the subleading terms are going to be suppressed with relation to the leading terms. And this is something that we always check, that having obtained the solution, you sort of check various terms of the expansions to see that they are reasonably, that higher orders are smaller. So here's the procedure. So you take the metric and then you write it in the Eddington-Finkelstein gauge, write down the field equations, impose the initial condition, pure ADS for early times, and then the boundary condition that, well, it approaches ADS solution at infinity, and then the only source is that of the sourcing function. Then you take the amplitude expansion of Bhattacharya and Minwalla, and on top of that, now each term here you also develop in a gradient expansion where you introduce a derivative counting parameter mu. So then you plug these to the field equations and try to solve iteratively at each order in these parameters. Then after obtaining a solution, then you must go back to Pfefferman-Graham coordinates and expand in one of over the radial coordinate to be able to use the standard formula to extract out the stress tensor. And that's it. And here are some equations that you find as a result. Here's the scalar field profile up to fourth order in gradients. Here's the energy density in the laboratory frame. Well, it starts at amplitude squared because it's quadratic in the fields. And this is a solution up to second order in gradients. So the first term is what Bhattacharya and Minwalla found, and this is the extra from this work. Okay, so now we would like to compare this with free streaming and viscose hydro. So what do I mean by free streaming? It's astonishingly simple. You just consider some phase-space distribution, and you want to follow its time evolution, and that gives you the stress tensor. And well, we assume that the phase-space distribution is factorized. This is a standard assumption. So there's some density profile which time evolves, and then some form factor. And again, in keeping with the previous picture, we take the evolution to be just in the x direction. And free streaming means just that the distribution stays the same, and it's just the location of the peaks that's moving. Now the details of this function doesn't matter because when you go to polar coordinates, well, okay, it doesn't matter because the k part of the integral you can do, that just gives an overall energy density factor in front, and then all that remains is just this density profile that goes in here. Now the density profile, on the other hand, you obtain by well, if you give the scalar field some initial source profile, then you have to read off from the ADS calculation that what's the density profile that you want to plug in here, and you plug it just after the injection, just after the sourcing is done. Okay, for second order viscous hydro, well, you have seen these equations before. This comes from the paper by Bayer et al. From 2007. Chris Herzog was talking about simulating 2+1 plasma in this context. So there's the ideal term and the viscosity term, and then at second order, well, the basic information there is that you want to preserve causality so that information is not flowing at the speed of light, but there's some relaxation time scale that gets introduced. And I mean, well, you want information to flow at finite velocity, and that it's associated with this time scale. Okay, so we don't do hydrodynamic evolution, but what we rather do is that we calculate the energy density and velocity from the ADS CFT, and then we assume that what if hydro would be valid, then that would mean that this is the equation that gives the stress tensor. So let's see if that's true, plug in the values into this formula and see whether the resulting stress tensor at any given instant resembles that you get from reading from the metric profile. Okay, so here are some figures. This is in the laboratory frame so that you can see that there's some flow. And initially we start with the Gaussian profile so that the energy and pressure components, or the T and Txx, the diagonal components have these Gaussian profiles, but you can see that there's some flow which increases in time, so this is early times, this is later times, but the evolution is very slow, so that there's not much interesting going on in these pictures. So what's more interesting to look is to go into the co-moving frame and then extract the different components of pressure in the x and y directions. Now, because the inhomogeneities were in the x direction, nothing in the y direction, so you expect to see some anisotropy in the pressure. And indeed, here it is, and you can see that it actually grows initially, so that the anisotropy becomes more pronounced. Now, here's a comparison. The solid curves are anisotropies calculated from the ADS CFT, so looking at the subleading behavior of the metric, stripping off the stress tensor, boosting it into the co-moving frame, extracting the pressures, so that's how you get the solid curves at earlier and at later times. And then the dashed curve comes from the free streaming model. And it works amazingly well. Now, on the other hand, if you want to compare with hydrodynamics, well, first you could try to compare with by checking what's the anisotropy given by the first order hydro formula versus the numbers that you get from the ADS CFT calculation. And you find that the matching is rather poor, and well, qualitatively it's okay. I mean, the curves have the similar shape. Again, the solid curves come from the ADS CFT, and the dashed curves come from hydro. But the quantitative matching is rather poor and becomes worse as time progresses. Now, if you include a second order hydro correction, that improves the matching to hydro at later times. Originally, it makes the matching even worse. Now you even lose now the dotted curve is the second order hydro curve. At early times, you don't even have qualitative matching. But at early times, on the other hand, the free streaming is matching very well. And at later times, you start to get first qualitative matching with the second order hydro, and then even the quantitative matching becomes rather good. So remember that what was the strategy in these heavy ion calculations? Take some initial energy deposition statistics from the color glass condensate model, then use free streaming to evolve that to the stage where you can where the evolution gives you the initial conditions for hydro evolution. So so first free streaming, then hydro, and the question was that whether that was sensible at all. So it seems that at least in these pictures, free streaming is a good matching even at early times, and then if you wait a little bit, then you start to have matching with second order hydro. Okay, so here's just a more complicated plot with 4 Gaussians at various locations and at different heights. The same story is there. First you have good matching with free streaming and very poor matching with hydro, and then the hydro matching becomes better.
But it seems like there's always good matching with free streaming.
Yes, that's true. So that's one of the puzzling features. Okay, well, I will get to the summary slide soon, but no, let's just go there. So, okay, so this was motivated by heavy ion collisions, and in particular by the event fluctuations, which are significant. So that motivated us to do this study of time evolution of inhomogeneities. And well, it seems to suggest, well, other works by using colliding shockwaves and so on, they point to fast isotropization and hydrodynamization in this strongly interacting plasma. And also we find that our results are consistent with that, we find that second order hydro gives matching at relatively early times, where we still can trust the perturbative approximation. And also the results are consistent with this free streaming to hydro picture. Now some puzzles are that, so why is the free streaming better? And why does it work so well? So there's been some discussions that we've been having about that, but let me not get into that. So it might be just an accident, so it might be that if you do a more complicated system, then you lose this feature. Well, it requires some further study. And then also the perturbative approach doesn't quite allow us to follow this conversion to second order hydro. So it could be that there's just this, that the matching becomes good at some point, and then it could become worse later on. So you would have to be able to follow this evolution for later times. So a future problem is to do a more complete study, perhaps with more realistic symmetries, and then most likely you have to do this with numerical methods. Now another thing that would be interesting is to see is that if there are any other physics contexts where these kinds of studies are relevant. And if you have any thoughts on that, I'd be happy to hear. Okay, so thank you.
Okay, any question? Yeah.
When you do these comparisons, right, it looks like the anisotropy grows with time, but eventually it should isotropize. Have you been able to follow it?
Yeah, same thing that you would think. I mean, of course, it has to isotropize at some point, but then on the other hand, it's kind of expected by the heavy ion people that this is what you would find, that first there's this growth of anisotropy. But again, same thing, that you would have to be able to follow the time evolution longer to see what happens.
The hydro should only really start working when you start isotropizing very well, right? So it's actually, is it surprising that hydro works so well here?
Well, on the other hand, we were working in the long wavelength expansion, so that the scale of spatial variations is large compared to the inverse temperature. Yes?
So, at very late times, the hydro should certainly be a good approximation, assuming that things do settle down. What's known about how free streaming either agrees or disagrees with hydro in that sort of late time limit? That should be an easy thing.
That's a good question. I actually don't know. Probably it would be better, then people would use that. So by that argument, I think that hydro is better.
And noticeably different somehow that they're.
Yeah.
Yeah, I have. Yeah, well,
Yes. So how the color glass condensation is encoded in this holographic picture?
It's not encoded at all. Well, originally what we hoped to be able is to like for instance in this case, the initial condition was this Gaussian peaks at different locations, and different heights. So the original hope was that we would take from these calculations by Müller and Schäfer some model for what's a typical initial state, and then take a typical profile as a starting condition, and then evolve that one, and then do this repeatedly to get some statistics, so that you would really get some result as to how our initial probability distribution for the energy deposition is changing through this early time evolution, so that then you would get a final probability distribution, and that would then be a kind of a realistic initial condition for hydro to use. But that's a bit more involved.
Let me ask as a final question.
Yeah.
Is there any possibility or any chance just to compare that with experiments in LHC?
Well, if we will be able to do what I just said, that take a CGS model for typical initial energy depositions, use this evolution, and then to come to the stage where the hydro takes over, then take some hydro code, evolve that further, and so on, then you would be able to get some predictions to compare with. Of course, this is not QCD and blah blah blah, but anyway.
Okay, so let's thanks the speaker again.